Hi, everyone. Welcome to the online Causal Inference seminar. Today, we have the pleasure of having a talk by Sofia Triantafyllou from University of Crete, who will be giving a talk on a Bayesian method for causal effect estimation with observational and experimental data. The discussant today is Shu Yang from NC State University. We hope you'll enjoy both of the talks today. Today's questions will be handled by Chingyuan. Please submit your questions in Q&A, and I will switch over to Chingyuan, who will fill you in on the rest of it.
Yes, so as Emma said, please use the Q&A box on the bottom of your screen to submit questions. This will help us monitor the questions and which question has been answered. Please do not use the chat box unless you want to communicate with the panelists directly. So I'll try to stop Sophia from time to time to take questions. And without further ado, Sophia, do you want to share your screen and start your talk?
Yes. Okay, let me share my screen. Okay, so thank you for the invite. It's lovely to be here. As Emma said, I'm Sofia Triantafyllou and I work at the University of Crete. And today I'm going to be presenting joint work with my collaborators, Greg Cooper from the University of Pittsburgh and Fatma Jabari, who is now at Microsoft. And the title of my talk is a Bayesian method for causal effect estimation with observational and experimental data. In hindsight, I think I should have named the talk a Bayesian method for predicting post-intervention outcomes, because that's what we're interested in this talk. So the motivation for this work comes basically from clinical settings where you may have patients and you want to decide what's the best treatment for every patient. So the idea is that we work, for example, with many doctors, many clinicians who work in critical care, and they have a lot of sepsis patients, and the new sepsis patients comes in and they want to predict what the chance of in-hospital mortality is going to be for that patient if they give them steroids versus if they don't give them steroids. So they want to compute a post-interventional distribution, the post-interventional distribution of the outcome of interest for their patient, given different treatments and given some other covariates that they may know for these patients. And in general, when they want to answer questions like this, they may have various data sources. So they may have observational data. Usually they have large cohorts of patients. They have historical data of large cohorts of patients that they've already treated. They've already given them steroids or not given them steroids. And these usually tend to have large sample sizes, and they measure a lot of covariates because it's the entire medical history of the patients. However, unfortunately, you cannot always use them to estimate post-interventional distributions because of possible confounders. And then they may also have some experimental data. For example, they may have data from randomized control trials that they have performed in their hospital or other people have performed in other hospitals. And these unfortunately have, they are unbiased for causal effect estimation, so you can use them to predict the post-intervention outcome, but they have limited sample sizes usually, and sometimes they also, particularly when they're done outside the system, the hospital system, they may be measuring a limited set of covariates, and they don't have the entire medical histories, for example, of the patients. So the work that we're trying to do, the question we're trying to answer is, you want to predict a post-interventional outcome for your patient, and what's the best way to do this prediction. We do assume we work in the space of causal graphical models, so we do assume that you have a causal structure. Let's say you have a graph, a causal DAG that describes the relationships between your variables, but some of the covariates may be unmeasured, right? And when we talk about what's the best prediction for your post-intervention outcome, essentially we view this, we're not so concerned in this work with what's the best statistical model, to what kind of distribution should you use, but we are interested, we view it as feature selection problem. So what are the best covariates to include in this model for predicting your post-intervention outcome, right? So here, for example, we have a hypothetical causal structure for sepsis, where you have some covariates related to your treatment, which is steroids, and your outcome, which is in hospital mortality. And the lifestyle and genetics are unobserved, so you don't measure them for your patients, but you do measure whether they have diabetes and their blood pressure. And the question is, which is the best set of variables to include in the model, in a model to get the best prediction for in-hospital mortality, given do of steroids. This is the classic way of using the do operator to model interventions in causal graphical models. So the talk goes through different scenarios for answering this question, essentially. So in the first part, we sort of talk about the theoretical properties that this set should have. If you know the causal graph, can you identify the best set of covariates to use in predicting your post-intervention outcome? And this also has, we discussed this problem in two different cases. So the first case is, in both cases, you know the causal graph, but in the first case, you have actually also access to the post-intervention distribution. So you have experimental data, you have data from a randomized controlled trial. And in the second case, you do know the causal graph, but you only have observational data. And in the second part of the talk, we're gonna, because usually in real world settings, we don't know the causal graph. We assume that we only have, you don't know the causal graph, you have observational data and experimental data or interventional data. I use these two words interchangeably in this to mean randomized controlled trial data, essentially. So in the second part of the talk, we're going to talk about what can you do, how can you select the best subset of covariates to include in your model if you don't know the causal graph, but you have these types of data. Okay, so just a bit of notation that I'm going to be using throughout the talk. In general, unless otherwise mentioned, I use Y to represent the outcome of interest, X to represent the treatment, and I'm assuming that I'm having a set of pre-treatment covariates Z. I'm only assuming pre-treatment covariates because essentially we want to predict the post-intervention outcome with the information that we have before assigning the treatment, because we want to predict what's the best post-intervention outcome given different treatments. And I'm using the red font to denote the experimental data, the experimental distribution, the parameters of the conditional experimental distribution. And DE is data from an experimental distribution, and DO is data from an observational distribution. And similarly, theta E are parameters for the experimental distributions, and theta O are parameters for the observational distributions. So there are some messages on the chat. I don't know if I should look at them. Is there something wrong, or should I go on?
No, no need to monitor anything.
Okay. Okay, so as I said, we want to predict which variables should you include in a model to predict a post-interventional outcome. Now, if you wanted to predict an observational outcome, if you weren't interested in doing post-interventional, if you weren't interested in predicting the post-interventional outcome, and you just wanted to predict, for example, whether a patient will die in the hospital, given the information that you have from them, including whether you have given them steroids or not. So this is just observational prediction of your outcome Y.
Sophia,
and you know, yes.
Just one short question we have in the Q&A on clarification on the previous slide about what is Z.
Z is yeah, that's right. Z is a subset of the pre-treatment covariates. Okay.
Yeah.
Okay, yeah, and in general, I'm using Z throughout the talk to talk about subsets of pre-treatment covariates, which are candidates for being the best set to predict post-intervention outcomes. So, yeah, as I said, we have a causal structure, and in general, we assume that there exists some acyclic DAG, but some of the covariates are not measured. So the causal relationships among our observed covariates are described by an acyclic directed mixed graph, and that's the setting that we are assuming. We have an acyclic directed mixed graph, pre-treatment covariates, and let's say we want to predict Y, we want to predict an outcome. So for this scenario that we just have observational prediction, there is an answer in which variables you should include. It's the Markov boundary of Y. The Markov boundary of Y consists, in the case of pretreatment covariates, from the parents of Y, the districts of Y, and the parents of the districts of Y. Essentially, it's every variable you can reach in the ADMG via a bidirected path, a collider path. Okay, and if you have the graph, you can identify it. It leads to the optimal prediction of your outcome under some criteria for optimality, like using a proper scoring rule and things like that. And you can also identify it if you have the distribution, you can identify it just based on the conditional independencies that it entails, right? So essentially, this set is the minimal set of variables that makes all other variables independent of your outcome. So it gives you the minimal, the smallest model that has maximal information for your outcome, right? Now, in our case, we want to predict post-intervention outcomes. So essentially, the graph that describes the causal relationships and that describes the factorization of our distribution is no longer the original ADMG, but it is the ADMG post-manipulation. So you have manipulated the intervention variable. So you have removed all incoming edges into this treatment variable. So your causal graph now is this post-interventional causal structure. And essentially, you want to predict these post-intervention outcomes. So basically, what you would like to include is the Markov boundary of the outcome in this post-intervention graph, right? So this is, we call this the interventional Markov boundary. And if you actually have samples from the experimental distribution, if you can actually estimate the interventional distribution, you can just use the post-intervention graph, identify the Markov boundary in the post-intervention graph, which is what we call the interventional Markov boundary. And this is going to be the minimal set of variables that makes all other variables redundant for predicting your post-intervention outcome. Okay, and here I'm just using the interventional Markov boundary consists only of the covariates, not of your treatment. Now, if we don't have the experimental distribution, let's say again, we know the causal graph, but we don't have the experimental distribution, and we only have the observational distribution, and we still want to predict our post-intervention outcome. So we want to predict the probability of in-hospital mortality given due of steroids. And we know the graph, but we don't have access to the experimental distribution. So the problem that the maximal amount of information is given by these two variables, diabetes and blood pressure. Ideally, we would like to estimate the probability of in-hospital mortality given due of steroids and blood pressure and diabetes. But the problem we're having now is that this is not identifiable from the observational distribution. So essentially what we want to do here is we want to have a conditional distribution for predicting Y given due of X and some other covariates. And we want to include as many covariates as possible to have the best prediction for Y. But we want this prediction, we want this probability to be we want this probability as an expression, as a formula of observational probabilities, essentially, because we only have the observational distribution. And if you condition on diabetes, for example, here, you open this backdoor path, so you cannot identify this conditional probability based on the observational distribution alone. On the other hand, you can estimate the probability of in-hospital mortality given due of steroids and blood pressure, because this is an adjustment set, so you can just estimate this as the observational distribution. So basically what you want here is the same as in the previous scenarios. You want the smallest set of variables that includes the maximal information about your post-intervention outcome. But you also want this conditional probability distribution to be identifiable from your observational distribution. And obviously, such a set of covariates may not exist. So, for example, if you hadn't measured blood pressure here and you had a confounder, an unmeasured confounder between your treatment and your outcome, none of the post-intervention probabilities would be identifiable from the observational distribution, right? There's no expression based on the observational probabilities to calculate these conditional probabilities of your post-intervention outcome. In this example, on the other hand, if you do measure if you do measure blood pressure, you can estimate the probability of in-hospital mortality given due of steroids and blood pressure. You can estimate the probability of in-hospital mortality given steroids by marginalizing over blood pressure, but you cannot condition on diabetes as well and estimate any of these probabilities. So this is called identifiability, the post-interventional probabilities that you can identify from the observational probability distributions. And it has received a lot of attention. There exist sound and complete algorithms in which you give them the causal graph and you also give them a conditional probability query, and it will return a formula for computing the post-interventional probability based on observational probabilities, or it will return that this is not identifiable, and these are sound and complete algorithms. Okay, so back to our problem. We want the minimal set of variables that have the maximum amount of information for our post-intervention outcome. And to answer this question, what should a set of covariates satisfy to be the minimal set of covariates that gives the maximum amount of information for your post-intervention outcomes? We came up with 3 conditions. We call this set, first of all, the causal Markov boundary, and this is supposed to be the best set for predicting a post-intervention outcome using the observational distribution. So basically, again, you want the smallest set of covariates that gives you the maximum amount of information, but also guarantees identifiability. So essentially, any set that is a causal Markov boundary needs to satisfy these 3 conditions. And I'm going to go through them, actually. The first one is just encodes identifiability. So if you have a set Z and you want every causal Markov boundary Z has to satisfy this condition, the probability of your post-intervention outcome given Z has to be identifiable from the observational distribution. And then the second condition tries to express the fact that this set has to be maximally informative. So this condition says that essentially, if you additionally condition on another set Z prime, then either this doesn't give you any additional information for your post-intervention outcome, or you lose identifiability. So essentially, there's no covariate that you could add to the causal Markov boundary that would give more information about your post-intervention outcome without losing identifiability. And then the third condition tries to encode minimality so that this set should be minimal. And essentially, this condition here says that you cannot remove any variable from the causal Markov boundary without losing some information. So this tries to shield you from situations like these. In this graph, for example, variable alpha satisfies the first 2 conditions of causal Markov boundaries. So you have identifiability. You can estimate the probability of Y given due of X comma alpha from the observational distribution. And you can also not add any other covariate without losing identifiability. So if you add B, you open this path and you lose identifiability. But on the other hand, it doesn't give you any information about your post-intervention outcome unless you condition on B. So whether you know alpha or you don't know alpha, it doesn't help you predict your post-intervention outcome. So this is a scenario where you have alpha, but it's not minimal. Alpha satisfies the first 2 conditions, but it's not a minimal set. So This condition just guarantees that causal Markov boundaries don't include variables like this. Okay. So these are the three conditions that so a causal Markov boundary should satisfy. As I said, the causal Markov boundary, the intent is that you get the best set to condition on to predict your post-intervention outcome when you have an observational distribution, so you cannot estimate anything you would like. And we have proven some things about these causal Markov boundaries. One of the things is that they are not unique, first of all. So you may have situations like these where here, for example, you can condition on D, and then if you condition on D, you can also condition on A, but you cannot condition on B and C. You cannot add them to the conditioning set because you would open this path and you would lose identifiability. And similarly, if you condition on B, you can also condition on C, but you cannot condition on A or D. So these sets both satisfy all of the conditions for being a causal Markov boundary. So, you know, which one of them will give you the best prediction of Y is, you know, up to the parameters of the distribution. You cannot tell them apart just by graphical criteria. Another thing that we have proven for causal Markov boundaries is that causal Markov boundaries are adjustment sets, essentially, when we're talking about pretreatment covariates only. So the question was, would it be possible that, you know, you had a set that you had identifiability for some set, you could identify this distribution for some set using observational probabilities, but not just by using rule 2 of do calculus, essentially, but you would need to use more complex rules or use other criteria like the front door criteria, or use a sequence of rules so that you would end up with a more complex formula. And the answer is no. So you essentially, that makes looking for causal Markov boundaries easier, because you just have to look for adjustment sets, basically, that satisfy these three criteria. Okay, and then another thing that helps when looking for causal Markov boundaries is the fact that we have also proven that they are subsets of the Markov boundary. So this may seem pretty obvious, but when we started thinking about it, it wasn't so obvious. Maybe to get identifiability, you would need to go beyond the Markov boundary of a variable. And this turns out not to be true. So we have proven that the causal Markov boundary needs to be a subset of the Markov boundary. So, you know, this makes looking for causal Markov boundaries easier. You need to look for adjustment sets that are subsets of the Markov boundary, essentially. And here's a summary. In this slide, you can see a summary of all the Markov boundaries we've talked about. So the first is the well-known Markov boundary. And this is the set that gives you the optimal prediction of a variable from the observational distribution, of an outcome from the observational distribution. The interventional Markov boundary gives you the optimal prediction for a post-interventional outcome from the experimental distribution, from the post-intervention distribution. And a causal Markov boundary gives you the best prediction for the post-intervention outcome from an observational distribution. And an interesting relationship between among all these three types of Markov boundaries is that if the interventional Markov boundary is a causal Markov boundary, so essentially if you have identifiability for the interventional Markov boundary, this only happens when the interventional Markov boundary is the same as the Markov boundary, minus X. Okay, so this is sort of the general characterization of Markov boundaries and causal Markov boundaries, which are, as I said, try to answer the question, which variables should you include in a model to predict your post-intervention outcome? And I think this is a good place to stop for questions before we move on to the second part of the talk.
Yes, there is indeed a very timely question, but it's from Robin Evans. Should that be MB of Y minus X? I guess this is what you just said.
Yeah. So Yeah, I've kind of abused the notation here because I write them kind of differently in the paper. I have them include the treatment, but it's not so clear to go through it in a slide because you have to introduce other sets or remove X from the set every time. But yeah, this is minus X. Sorry for the type. I should have corrected it here.
Okay, yeah, that's all we have at this point.
Can
Okay.
I ask a little question? I was just wondering. So, what if you have data or distribution that is not observational, but also not experimental of interest? It's like experimental on a different variable. Could you treat that as like having observational distribution still, or wondering?
I think, well, I think that's an interesting question because ultimately what we want to do with this is to be able to combine different types of data, so probably different types of experimental data. But I think that would require for a different, like, you know, it's a whole different. I don't think that I can answer that. I think you could. I don't think that you could treat them exactly as an observational distribution. You could model the differences, I guess, and you know, by looking at the graph, you could figure out. Yeah, you could figure out what you can identify from this different experimental distribution with respect to the experimental distribution you want. But I think that's a complex question and doesn't have an easy answer that I can give right now. But it's a great area of work, in my opinion. So.
Yeah. There's more questions.
Yes,
Should
we received more questions.
Okay.
Maybe just take one or two more. So this one is from Alexandra Drawing. Sorry if I mispronounced your name. Would the IMB also be a subset of the MB here? Just like the first.
IMB is a subset of the MB, yes.
Okay, great. Another question from Lanfrika admin. Is there a code base that allows one to get the causal Markov boundary? As someone who's interested in implementing this, how can I go about it?
Okay, yeah. So there's no algorithm except from the brute force algorithm. So you could just find the Markov boundary, just using the algorithm for finding Markov boundaries, and then look at the subsets and look at which subsets. So these essentially are the conditions are dependencies and independencies in reality. So you can just take the Markov boundary and take every subset of the Markov boundary and check if they satisfy the conditions. Apart from the first condition is identifiability. So you could run Spitzer's algorithm, the ID algorithm, to get an answer on whether the probability of y given 2 of x comma z is identifiable. And then the remaining two conditions just amount to conditional independencies that you can read in the graph.
So it sounds like there's no currently no
there's no
package that,
smart algorithm. I don't remember if in the paper, I mean, I had an implementation for taking, but it wasn't the main focus of the experimental section of the paper. So I'm not sure if it's on the. I have some code that's related in my GitHub. That's the UAI paper of 2021. But you can email me and I'll whoever you are.
Sounds good. Maybe just one last question. Why the name quote Markov boundary? Why do we call it Markov?
The original Markov boundary was not named by me, obviously, and then I just kept that was my inspiration. So I just thought that these are different types of boundaries. I think, you know, causal Markov boundaries are not boundaries in reality because they don't shield you from the rest of the graph necessarily. But anyway,
yeah, that's fine. I think this is probably Pro's invention, isn't it? Anyway,
yeah,
maybe.
The first one is Pearl's invention. The last two are I named them, but it was just based on, you know, I'm trying to do something similar to Markov boundaries for a different setting, which is predicting post-intervention outcomes. Okay, great. Should I go on?
Yes, please.
Okay, how much time do I have?
You have about 15 minutes left.
Oh, okay. Okay, so what happens if we don't know the graph? So in the general settings, you're not going to know the graph, and you want to predict your post-intervention outcome. So we assume that we have observational data measuring your treatment, your outcome, and some covariates for some samples, and then experimental data measuring again your treatment, your outcome, and some covariates for a much smaller number of samples. That's what we assume. And essentially what we want to do, if we don't know the graph, the general idea is that I want to find a set Z that optimizes the prediction for Y given do of X. And then if this set Z prime, Z star, as I call it here, also happens to be an adjustment set, I want to use the observational data to compute this conditional probability distribution. If it's not an adjustment set, I just want to use the experimental data because the using the observational data will give me a biased estimate for this conditional probability distribution. So just a reminder, this is a reminder of the notation because I'm going to start using the experimental and the observational parameters here. And these are parameters for a given set Z. That's how I begin. Let's say for a given set Z, you want to decide, you have observational data and you have experimental data, and you want to decide whether Z is an adjustment set or not. So that's the problem that we're trying to solve in the next set of slides. So in order to do that, we define two different variables, essentially. These are not variables, these are events more of, we define two different hypotheses. This stands for the hypothesis that Z is an adjustment set, and this stands for the hypothesis that Z is not an adjustment set. So these are two complementary hypotheses. And essentially we want to, if HZA holds this one, then we want to use the observational data to estimate the conditional distribution of the post-intervention outcome given Z. If HZA bar holds, if Z is not an adjustment set, so if this assumption, if this hypothesis holds, we cannot use the observational data for this estimation. We can just use the experimental data. So basically, we have the observational data and the experimental data, and we want to use them to estimate the probability that Z is an adjustment set. And we can write this probability as the probability of that Z is an adjustment set given just the observational data times the probability that you see your experimental data if Z is an adjustment set and if you have already seen the observational data, and then you normalize using these two probabilities. So that's how you estimate. In order to estimate the probability that Z is an adjustment set, you need to estimate these four quantities in the numerators here. And I'm just going to talk about this part and this part. This part is sort of how much do you believe that Z is an adjustment set or Z is not an adjustment set when you've just seen the observational data. There are ways to compute that, but in this formula, it doesn't make much difference because even for small experimental sample sizes, this part here, which is sort of the marginal likelihood of your experimental data, dominates this product. So I'm just going to talk about this part. So this part here is the probability of seeing your experimental data if Z is an adjustment set and if you have already seen your observational data, and you can just integrate over all possible parameters, and this is then the likelihood of your experimental data, your likelihood of your post-intervention outcome, essentially, given this set of parameters. And this is the density of these parameters, given that Z is an adjustment set and given that you have already seen your observational data. Okay, and then you just need to compute this integral. So this is sort of a posterior for the interventional parameters, given the observational data and given your hypothesis that Z is an adjustment set. So basically the basis of this computation is that if this hypothesis is true, so given this hypothesis, the experimental and the observational parameters are the same. The experimental parameters and the observational parameters for the probability of Y given do of X comma Z. This is the same as the probability of Y given X comma Z. So these parameters are the same. So you can sort of instead replace these experimental parameters here with the observational parameters, and this is just the posterior for these observational parameters given the observational data. And this is the likelihood for your post-intervention outcome, for your experimental data, given the observational parameters. And this ends up being just a marginal likelihood that you can compute in closed form for many families of distributions. Now, on the other hand, if under the complementary assumption, under the assumption that Z is not an adjustment set, the observational and the experimental parameters are not the same, we make a kind of stronger assumption here that the observational data don't give you any information for the experimental parameters, so you can just use a flat prior. This is not exactly true because it could be possible, that you cannot get a point estimate for these parameters if Z is not an adjustment set, but you could possibly bound them or get a different posterior. But here we just assume that the observational data give you no information for your experimental parameters. And then this again becomes a marginal likelihood that you can compute. This is just a flat prior, and you can again compute it with many in closed form for many different distributions. So now that we have computed these two scores, these are essentially, as I said, marginal likelihoods from our experimental data, in one case using the observational data to build the prior, and then in the other case, we don't use the observational data to build the prior. And we can substitute it in these equations and just compute the probability that Z is an adjustment set based on the observational and the experimental data. And we have also proven for, so in general, in this talk and in the work that we've published, we use discrete variables and multinomial Dirichlet distributions. So for this setting, for discrete distributions, we show that this probability computed that way using the marginal likelihoods will, it's consistent, so it will go to 1. It will converge to the true data generating model. So it will go to 1 if Z is an adjustment set and to 0 otherwise. Okay. And then we have a version of our method where we allow the observational data to have some additional covariates. So, it could be, we have settings where the experimental data measure fewer covariates. So these are ZB, you have a set Z. In this set, you have some variables, ZB, that are measured in both the observational and the experimental data. They are shared. And then these ZO variables are only measured in the observational data. And then again, we want to use the same method to see if the variables, the entire set Z is an adjustment set. So the variables that are included only in the experimental, in both the experimental and observational data, and the variables that are included only in the observational data. And the method is pretty similar, but essentially here, if you want to get this density for your experimental parameters under the assumption that Z is an adjustment set, the experimental parameters that you're going to score the experimental data with only include ZB because you haven't measured ZO in the experimental data. So you basically, these experimental parameters are computed from the observational parameters using the adjustment formula. So under the assumption that Z is an adjustment set, you can just use the adjustment formula and get the probability of Y given do of X, comma, the variables that you have observed in the experimental data. And this gives you the parameters that you're going to use to score the experimental data. And this is a bit complex, but in any case, the idea is that, this is what you want to compute. And the way these parameters are connected to the observational parameters is using the adjustment formula. So basically, the method that we have learns the posterior distribution of all of these parameters from the observational data, and then you sample from this posterior and you use the adjustment formula to compute the experimental parameters, and then you use these experimental parameters to compute the likelihood of your experimental data. And this is just because you cannot compute this integral in closed form, and that's why you follow this sampling process to estimate the probability of Z being an adjustment set. And the reason we care about that is that the observational data may include some additional covariates which are important for predicting our post-intervention outcome. And this way, if you decide that you have this additional covariate in the observational data that looks to be like an adjustment set, you can just include it in your prediction for your post-intervention outcome. Of course, this comes with additional assumptions. This is not so. First of all, you need to assume that these two populations are the same, so you don't have differences in the distributions of these covariates in the experimental data when they are where they are missing. And also, you also need to assume that this equation, the adjustment formula, essentially only holds for sets that satisfy the adjustment criterion. So you need to assume some kind of adjustment faithfulness. But in any case, this is the high-level idea that you can also perform the same method, but allow the observational data to have some additional covariates. Okay. So now you have, for every possible set Z, you can compute the probability that this is an adjustment set. Z may also include some covariates that are not in the experimental data. And you can compute this probability that Z is an adjustment set. And then how are you going to predict your post-interventional outcome, and how are you going to select the best Z? Because you have many Zs for which you have made this estimation. So if Z is an adjustment set, you can use the observational data and make some estimation for your post-intervention distribution. If Z is not an adjustment set, you could use the experimental data and get a different estimate. Which one should you pick? In our case, we're just taking the weighted average. So we take a weighted average of these two estimators weighted by the probability of Z being an adjustment set and Z not being an adjustment set. And then so for every set, for every possible set, we have an estimator for the conditional distribution of the post-intervention outcome given that set. And the way we pick the best set is by defining a metric for performance that we care about. So here, for example, we're using the log loss, but we have also implemented this for accuracy and expected utility. And we estimate the expected performance of this set in predicting the post-intervention outcome. And then we select the Z that optimizes this performance metric. Okay, so this is our method. We call it overlap because we allow some overlapping variables. And I don't know if I have much time. I have a few results to show very quickly. 2 minutes? Okay, I'll try to do it in 2 minutes. So I have very toy examples just to show what this method can do. So assuming that this is the true network here, and you have measured X, Y, and W in both the observational and the experimental data, but you have this hidden confounder, right? So you cannot use the observational data. You want to use the experimental data and estimate the probability of Y given to of X, W. You cannot do this. You cannot estimate this quantity from the observational data because you have this confounder, right? So our method is overlap. It's the blue one. The red one is using the observational data, and the yellow one is using the experimental data, and the green one is just an older version of our method, so forget about that. And we can see here the x-axis is the actual bias of the true bias induced by the confounder, right? And the y-axis is the performance of the method. The lower, the better. This is distance from the ground truth log loss. So we can see here that the bigger the bias induced by the confounder, the worse the observational data do. The interventional data do fine, and our method also does fine, okay, without knowing whether there is a confounder or not. And then in the second case, we simulate data from the same graph, but this time you measure Z in both data sets, but you only measure the W in the observational data. So you have an additional covariate in the observational data that you would like to use to improve your estimation of your post-intervention outcome. And this here the x-axis is how much more information W gives you about Y. So how much better you can predict Y given do of X if you include W versus if you don't, and you only include Z. So here, by using our method or by using the observational data, you do pretty well, and then you don't do as well using the interventional data because you lose some information because you haven't measured W, right? So the main point is that in these two situations, you don't know whether you should use the observational data or not. But if you use our method, you kind of overcome this problem, and you always get the best of both worlds. And the last slide the last example I wanted to show is how our method can also identify unbiased, but I'm going to just skip through it because I wanted to just mention, since I only have a minute or 30 seconds, that we have some funding to actually apply it in real trials, in real world settings. So we have some money from NIH. We have a grant approved to apply these methods in remap trials. Remap trials are some special kind of trials that are randomized, embedded, multifactorial adaptive platform trials. The key word here, I think, is embedded, because this means that they happen in the same hospital system as the observation, in which the observational data are gathered. So you don't have to do a lot of data harmonization between the experimental and the observational data, and you also have pretty similar populations, with the biases that come with participating in a randomized controlled trial and stuff, but still they're not, at least in completely different systems or places. And we have two specific sets of data and RCTs that we are going to use. And that's it. These are the papers that I have presented in this work, particularly the last two. In the UAI 2021 paper is the paper that talks about causal Markov boundaries, and an upcoming paper in AI and statistics talks about deciding whether something is an adjustment set or not based on observational and experimental data. And if you are intrigued and you want to know more about remap trials, this paper by our collaborator Derek Angus is a very good, and his collaborators, is a very good start. So that's it. Thank you. And yeah, I want to acknowledge our funding. And I also did part of this work when I was visiting the Simons Institute as a visiting researcher. So thank you very much. And this is another good place for questions, I guess.
Yes, thank you, Sophia. In the interest of time, we're gonna move straight into discussion, and maybe if we have more time at the end, we'll take questions then. Yes, Shu, are you ready to?
Yes. Can I share the screen?
Oh, I should stop sharing. Sorry. Okay.
Okay. Can you see the slides okay?
Mm-hmm.
Yes.
So thank you, the organizers, for the invitation. It is my great honor to be here to discuss Sofia's work. So for today's discussion, here is an outline. So I will first talk about randomized experiment versus observational studies, existing integrative approaches, and also I will recall a causal inference paradigm to see how randomized experiment and observational study can play a role in such paradigm, and Sofia's unique contributions. In the end, I will have a few questions for Sofia. So by now, it is well recognized the complementary features of randomized experiment and observational studies. So this table contrasts their unique strength and also limitations. So randomized experiment has been regarded as the gold standard because it has a randomization of treatment. However, they can be expensive, they have a shorter follow-up, they include a smaller and a less diverse patient population. One study showed that there's only 8% of cancer patients participated in oncology trials. So in this case, the randomized experiment is quite limited. And observational studies show some advantages over randomized experiment. So for example, they are cheaper, they include a longer follow-up, they include a larger and more diverse patient population, but there are many concerns such as unmeasured confounding, differences in the definitions of variables, and so on. There is actually a growing literature developing integrative methods that combine randomized experiment and observational studies, striving for the best of the two worlds. One line of research leverage observational studies in experimental data for improved generalizability of RE findings, or improved efficiency of the RE estimates with methods coming from both the frequentist and the Bayesian approaches, or identification of long-term treatment effects leveraging the surrogate outcomes in both observational studies and randomized experiment, and many others. Another line of research tries to leverage a randomized experiment in observational studies for benchmarking observational estimates or methods. So for example, we can use a randomized experiment to identify and estimate the bias function or the confounding function in observational studies. In today's talk, we have seen a different goal, right? So Sofia's method aims at identification of the best predictors for the interventional prediction. So that is the optimal covariate set Z star that predicts the Y given to X, the distribution the best. So some of the methods here are covered in our review paper. So, but I have to admit that the methods covered in this paper is far from complete. This is because nowadays, every day there's a new paper on similar topics. So this is quite active and involving area. So now let me recall a typical causal inference paradigm. We typically start with a causal inference estimate. This can be defined based on potential outcomes or the causal graphical models. Because this is not usually identifiable, so the very first step is to invoke certain causal assumptions, right? So we can identify the causal estimate as a statistical parameter, and then it becomes a typical statistical problem, right? It involves positing statistical models, fitting the model with the data, constructing estimators, and constructing inference procedures. In the typical setting, we cannot verify the causal assumptions, but in the data integration context or the data fusion context, when we have experimental data, somehow we can verify or falsify such causal assumptions for observational data. So for example, typical assumption is the ignorability of treatment assignment assumption. So because we have randomized experiment, so this assumption typically hold for a randomized experiment, but this might not hold for observational studies, right? So we can use the randomized experiment to verify or falsify such assumptions for the observational data. But the question becomes, there can be different sets of covariates we can condition on to assess such assumptions, right? So which covariate set should we use to assess such assumptions? This is where Sofia's talk comes in. There are two major contributions in my viewpoint. Firstly, Sofia introduced the concept called causal Markov boundary in the causal graph and discussed the relationship with Markov boundary, inventional Markov boundaries. This helps clarifying the following questions. First, whether the ignorability of treatment assignment is plausible in observational studies, right? And if so, which set of pre-treatment covariates is optimal? And thirdly, whether there are multiple such sets available. But this discussion is available when you have causal graphs, right? And we know that in practice, inferring the causal graph is very difficult. So the second contribution of Sofia's talk is the overlap algorithm to estimate the best set Z star without knowing the causal graph. So I try to summarize the algorithm in 4 steps according to the causal inference paradigm. So the first step is involving the causal assumptions. So for given Z, the null hypothesis is that Z is an adjustment set in observational studies so that the interventional distribution given Z can be inferred from the observed data. And the first step assess the plausibility of such null hypothesis by this conditional probability of the hypothesis given the observed data. And then in the second step, it involves a weighted combining rule. So if the null hypothesis is true, that means it can integrate the experimental data and observational data to jointly estimate the interventional distribution. Otherwise, it only uses the experimental data to estimate the interventional distribution, right? And the weight here is the conditional probability of the underlying hypothesis given observed data. So this is quite intuitive. And then the third step is to iterate step 1 and 2 and choose Z star that maximize the certain prediction performance. Now we have the Z star for the future in V2. So based on their Z star, we can do prediction, right, about their treatment and make some decision. So the algorithm is quite elegant, but I have a few questions for Sofia, so that try to improve the utility of the algorithm in practice. So let's go to the questions step by step. So the first step is about assessing the causal assumptions. This is feasible by exploiting the known intervention distribution from randomized experiment. But there are certain causal assumptions that are invoked, which might be stringent in practice. So for example, this assumption, so Sofia assumed that randomized experiment and observational studies have the same underlying population, but we know that study heterogeneity is quite common, right? You can imagine that the underlying population of RE and observational studies can be different. Have you considered about such a situation? One possible solution is using the selection diagram. So here it has a node S, represent the starting indicator. And using S, we can encode different assumptions for different populations. I think this may be some promising tool. And then the second assumption is assume the observational studies measure a richer set of covariates than experiment. But in practice, it can be the other way around, right? So the experiment and the investigators may measure different sets of covariates that are not typically done in real settings. So in this case, a randomized experiment and observational studies may have different covariate set, or the two studies have different measures for the same variable, right? For example, in clinical settings, there are two common scores for overall health status. So for example, a Charlson comorbidity score with the scales from 0 to 37. And the ECOG performance status is another common measure with the scale from 0 to 5. So if your causal diagram or the overlap algorithm can handle such cases, it will be quite useful. For the second step, Sofia took the Bayesian approach. So Bayesian models are quite flexible and attractive in complex problems. However, fully parametric models are very sensitive to model misspecification. So my question here is about model assumptions for the target and also nuisance parameters. Now, the target parameter is the interventional distribution given Z, but I feel there may be some issues with the model compatibility when you have different sets of Z's, right? A well-known example is a logistic regression, which cannot be collapsible. For example, logistic regression of Y given X, Z1 and Z2 might not imply a logistic regression of Y given X and Z1, right? So have you encountered such problems in the Bayesian computation? Also for the nuisance parameters, should we robustify models for the nuisance parameters because they are not of the primary interest, right? In nowadays causal literature, people try to construct estimators that are robust to nuisance parameter estimates. So this might be some interesting topic. Now for step 3, so you choose a Z star from a candidate pool that maximize the prediction performance. The question is, where does this candidate pool come from? Should we enumerate all possible Z's? Is it scalable when you have a pretreatment covariance, which is high dimensional, right? If not, what are the practical suggestions you have? Now, in the very last step, so we can use Z star, the inferred Z star, to do prediction for a future patient, right? And for decision making, uncertain quantification is quite important, but we need to take into account like various sources of uncertainties. For example, the causal model selection, so that is the selection of Z star, right? And secondly, statistical model fitting and estimates. I feel post-selection inference is quite difficult in frequentist world. So I was wondering, does the Bayesian framework offer a natural solution to this question? So in the end, I thank you for the opportunity to discuss this important work, and I congratulate the authors on this thought-provoking work, and I look forward to hearing your comments and seeing some future developments along this work. In the end, I have some references I mentioned. Thank you.
Thank you, Shu, for the wonderful discussion. Sophia, would you like to take maybe a couple of minutes to respond?
Yeah, sure. Thanks. That was a great presentation, actually. Can we see the slides just to go through the questions?
Yeah, sure.
That was actually a really accurate presentation of my work. So thanks. And so basically, yeah, these are very good questions, actually, all of them. We do assume that they have the same underlying population. Essentially, if you don't have, this is more of a more important assumption if you assume that you have overlapping variables. So if you allow additional covariates in the observational data, otherwise you just need to. The main assumption is that an adjustment set in one population is also an adjustment set in the other population, which is perhaps a bit easier. But if you allow the observational data to have additional covariates, then this is a very strong assumption. And we actually have, in the first paper that we published, we did kind of model for the selection bias, not any type of selection. So we didn't have these selection diagrams. We had selection bias that occurs due to the admission criteria for the randomized control trial. So not every patient is eligible to participate in the randomized control trial, and this can be represented using selection in graphical models. But so by using the variables that were selected upon. So I think this actually is a great big area of work, how to combine, because ultimately what we want to do is we want to combine, as I said to Emma, we want to combine many different, I think the benefit of using causal graphs is that you can combine many different and model many different types of subpopulations and experiments and things like that. So I think, yeah, that is absolutely the next step, trying to model selection biases using or different populations using things that you know or things that you can infer from the data. And then if the question 2, I didn't answer question 2, I think. So for example, yeah, your second question is actually very interesting. If the covariate sets have different measures, this is something that we do come across pretty often because we work with real world data, and this is a big problem. Even the way that people in clinical settings compute the same score for different patients may be different for very reasons that I had no idea of before I started working on this. So this is a very interesting, a very good question. I think that's why we, in a first approximation, we want to work with remap trials, because they are measured in the same hospital system, so you don't have this problem.
Hi, Sophia and Anshu. Sorry to interrupt you. We're really over time. So if you can give short answers to these questions, that would be great.
Yeah. I think this is also a great area to model with causal graphs. We have only used so far like very closed exponential curved exponential families of distribution. So in particular we've just used Gaussian and discrete variables. So this problem has been, we haven't really worked on this. This is also a work in progress that we are trying to extend these models for logistic and ordinal regression models. The next one is, yeah, enumeration. yeah, actually, the first part of the talk just hinted to some ways you can make this easier by just looking in the Markov boundary, for example. But yeah, you still would need to enumerate all possible z's, or maybe you have some z's in your mind that are very plausible because you work with clinicians, so they could give you some z's. Other than that, I think efficient algorithms based on some greedy adding covariates to the conditioning set would be an obvious choice, but I haven't worked on that at all, to be honest. I think that's it. Oh, okay. Yeah, post selection inference. I haven't really. I don't really know. I'm not sure about that. I don't think I have an answer for that. I think I know that's an issue. I don't know. The causal model selection in our case, we don't select an entire network, right? So we just select a Z. I'm not sure how post selection inference influences this.
But by chance, this star can be wrong, right? Cannot be.
Yeah, you could. Yeah, that's true. It could be wrong, and you could try to be Bayesian about that as well, and not select a single Z, but different Z's with different probabilities, right? And I don't know if this would solve the problem. I'm not sure. But maybe you could.
In the interest of time, maybe Emma can just conclude, and maybe we can take the discussion further after the formal session.
All right, great. So let's wrap up. Just 1 second. Okay. Thank you, Sophia and Shu, for actually great talks, great discussions. That was a really cool summary of the work, Shu, and many interesting directions to follow this in the future. We also received a large number of questions, many of which did not get answered. Not to worry though, all of those will be forwarded to our speakers. And so this is a great moment if you've asked many questions to maybe email with the speakers and start a collaboration if that is of interest. Anyway, next week we'll have student talks. We'll have a talk by Melody Huang from UC Berkeley and a talk by Tobias Friedling from University of Cambridge. We hope you all join us for those talks next week, and I hope you have a great rest of your week. Thank you all.